Alright, this video is called the Binomial Model and Beyond. So we're going to briefly talk about the binomial model and how we can morph it into the normal model. Well, first off, to kind of understand everything I want to go over today in this short video, I want to talk about a simple thing, okay? And that simple thing is this. I'm trying to get a red M&M. And I have read that the probability of getting a red M&M is 20%. So 20% of M&Ms are red. I found out that is the probability. So now, in order for this to work, in order for us to talk about the binomial model, the first thing we have to talk about is what's called Bernoulli Trials. Okay, and I'm going to write that down. Bernoulli. Let me make sure I'm spelling this right. There should be an O in there. Sorry, Bernoulli Trials. Okay, now to officially be called a Bernoulli trial, you have to meet three criteria. The first criteria is that only two possible outcomes are available. Only two possible outcomes. And the first outcome we would consider success, and the other outcome we would consider failure. So we got P, that's the probability for success. And then we got Q, and that would be the probability for failure. So in our case, success is, yay, won, I got a red M&M. And failure would be, no, I got anything other than a red M&M. The second criteria for a Bernoulli trial is that the probability of success is constant for every trial. So probability, I have a little spelling error there, probability of success stays constant. So if there's a 20% chance of getting a red M&M, then that's going to stay 20%. It's not going to fluctuate, or it's not like the M&Ms are going to learn and start changing color and things are going to change. They're going to stay constant. Okay. The last thing is that the trials themselves must be independent. And by now, hopefully, we know what independence means. That means that the result of one trial does not affect results of another trial. So if I get a red M&M, that doesn't make the next M&M become more or less likely to be red. Now, I want to talk about that independent real quick, because not every time do we know that it's truly independent. Sometimes we have to assume it. And when we assume this independent condition, I mean, if we're told, that's great, but sometimes we have to assume. And if we're assumed, we have to follow something called the 10% condition. Now I want to explain the 10% condition in as simple a way as I can. Now, imagine if I only had 10 M&Ms. That's it, just 10. Well, obviously if I choose one red one the first time, the chance of the next one being red is going to go down. Or let's say I even choose two red ones. So if I got 10 M&Ms and I choose two of them and they're red, then the chance of another one being red probably will go down because you only have 10 M&Ms. And when you take away two M&Ms from a group of 10, you have dramatically changed the outcome of what can happen next. Okay, so when you only got 10, taking 2 away makes a major difference. Now think about taking 100 out of 1,000,000. So you got 1,000,000 M&Ms and you take 100 of them and they're all red or whatever. Does taking 100 out of 1,000,000 really change a whole lot of things? Well, I mean, not really. If you want to look at it by the numbers, sorry, this keeps coming up. If you want to look at it by the numbers, think of 2 out of 10. So 2 out of 10 M&Ms, that represents 20% of the M&Ms. That's quite a bit. Whereas 100 out of 1,000,000 is only 0.0002 or 0.02% of the M&Ms. So not a huge chunk of those M&Ms, a very, very small proportion of those M&Ms. So the idea is this. As long as n, the number of M&Ms we're choosing, is less than 10% of the population, we are okay to assume independence. And that means as long as the amount that we're taking away from the population is less than 10%, then we're not taking so many away that we're going to make a major impact on the results. So for example, 2 out of 10, that's 20%. You're taking away 20% of all M&Ms. If there's only 10 of them, that's going to make a major difference. Whereas if you take away 2 out of a million, you're not really making a major chunk there. You're not really making a major change there. So as long as the amount you're taking away is less than 10% of the population, then we can still assume independence. That's what we need for a Bernoulli trial. All right, so now let's kind of move on to talking about actual problems that deal with this in the binomial model. Okay, so first couple things we could ask are some general things like what's the probability that the first M&M that's red, your first success, is the fourth M&M? Okay, so our first success. So we're looking for our first success on the fourth M&M. So I got this big batch of M&Ms, and I'm just going to keep looking through them. And, I want my first red one. Remember, success is getting that red M&M. I want that first success to happen on the fourth M&M. So that means that the first M&M was, not red. And then that means the second M&M was, not red. And the third M&M was, not red. And then finally the fourth M&M was my red one. So the 80% chance of not red, and then a not red, and then a not red, and then finally I get a red M&M on the fourth M&M. So multiplying that out, you could do a little shortcut obviously by doing 0.8 raised to the third times 0.2 is 0.1024. So you got about a 10% chance of getting your first red M&M on the fourth M&M. That makes a whole lot of sense. That's pretty easy. Okay. Now what if we said something like this? What's the chance that your first success is on the third or fourth M&M? Okay, so now we're talking about or. Remember, or means add. So we want to find that it happens on the third or it happens on the fourth. So it happens on the third. That would be, let's see here, that would be 2 failures. So I'm going to use exponents to make my work a little easier here. 2 failures, and then my third one is a success. So this is it happening on the third M&M. So fail, fail, success. Okay, so it happens on the third M&M. Or the fourth M&M, so we kind of already saw that up here, that would be 3 failures followed by finally a success. So failure, 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 success. Okay, so basically it would be taking 0.8 raised to the second times 0.2 plus 0.8 raised to the third times 0.2, and we get a grand total of 0.84. And I'm just going to double check that work. And, that is wrong. Sorry. Of course I made a mistake. I hit a plus sign 7 times sign, so I apologize. Not 0.84, 0.2304. 0.2304. Okay? Now, the last question I want to add dealing with the first success is, if you're thinking about this and you're trying to think ahead of time, okay, how many M&Ms would I expect to need to look at to get my first red M&M? How many would I need to expect to look at to get my first red M&M? Well, 20% is my chance of getting a red M&M. So my chance of success is 20%. That means 20 out of 100 M&Ms are supposed to be red. That's not necessarily going to be true because everything varies. We know that. But 20 out of 100. So if I reduce that, so let's think here. How many are supposed to be I'm trying to figure out not 20 out of 100. I'm trying to just look for my first success. So it would simply be really easy, actually. All you got to do is take 1 divided by 0.2. 1 divided by 0.2 is 5. So that means I would expect to look at 5 M&Ms to get my first red one. So I would expect it to take 5 M&Ms to get my first red M&M. And again, it's very simple. It's just 1 divided by your P, your chance of success. Very, very simple formula. Now, anytime you're dealing with a first success, you're looking for a first success. That's technically called a geometric probability model when you're looking for your first success. Now, the moment you give a set number of M&Ms, it becomes binomial. So, for example, if I said, okay, I have 13 M&Ms, right? 13 M&Ms. And I still have that same chance, 20% of getting a red M&M. Now, all of a sudden, I limited myself because now I have 13 M&Ms. I'm trying to find, red ones, right? So now this becomes binomial because I have a set amount of M&Ms. Okay, I'm not just looking for the first. I have 13 M&Ms set. So here we can ask you a question like, what's the probability that you have exactly 2 2 red M&Ms out of 13. So this is where we got to use our binomial model. So we have 13 M&Ms, choose 2 of them to be red. That's 2 successes, so 0.2 squared. And then I would have 0.8 to the 11. So 11 failures, 2 successes. Now, order matters here because I could have to be the first 2, the last 2, the middle 2, any set of 2. And that's what that 13 choose 2 is going to get me. So 13 choose 2 is going to tell me that there are, believe it or not, 78 different ways that I could have 2 reds and 11 non-reds in a group of 13 M&Ms. So to get my answer, I'm going to do 78 times 0.2 raised to the second times 0.8 raised to the 11. And I get that there is a 0.2680, or about a 27% chance that you're going to get exactly 2 red M&Ms out of 13. Now, hopefully that makes a lot of sense. Now, we could also talk about another example here where we say, what's the probability that you have at least 7 red M&Ms. 7 red M&Ms. At least. Remember, at least means 7 or more. So this means 13 choose 7, or 13 choose 8, or 13 choose 9, or 13 choose 10, or 13 choose 11, or 13 choose 12, or 13 choose 13. That sounds like a lot of work to do, and that's where we can have our shortcut on our calculator a little bit here. So basically, I'm going to need to do one of 2 things. I can do 13 choose 7 all the way up, or I could do 13 choose 0, 13 choose 1, 13 choose 2, 3, 4, 5, 6, right, or all the way to 6, 13 choose 6 and down. So you got to think of this as split 2 ways, right? I got 13 M&Ms. I'm looking for 7 or more. So I can actually do the work to find 7 or more, and that's 7 all the way to 13. Or I could do the work, which would be doing 6 or down to 0. Now, I'm looking for at least 7, right? I'm looking for 7 or more. So I could just simply do that work for 7 or more M&Ms. That's 7, 8, 9, 10, 11, 12, 13. Or I could do the work for 0, 1, 2, 3, 4, 5, and 6, and then just get rid of that. Because remember, if I find this, 0 through 6, and then do 1 minus that, I'll be left with what I want. So you got to determine what you want to do. Now, the idea is both of those are going to take considerable amount of work. Both of them are going to take many calculations. So if I use my calculator, I could use this feature called binomial CDF on my calculator. Now, what binomial CDF is it'll calculate the amount you want or lower. It doesn't do higher. So what I'm going to have to do is I'm going to tell binomial CDF that I have 13 M&Ms. Chance of a red one is 0.2, and I'm going to put a 6 here. Now, binomial CDF will accumulate 6, 5, 4, 3, 2, 1, or 0. It does not go up, so I can't put a 7 there and expect it to do 7 to 13. So that's why I need to do 1 minus this. That way, this is going to calculate 6, 5, 4, 3, 2, 1, 0, and I get rid of that by doing the 1 minus that, and I'll be left with what I want. So 1 minus a binomial CDF, 13 M&Ms, 0.2 is the chance that I find a red one, and I'm looking for 6, 5, 4, 3, 2, 1, or 0. And this probability, once I do 1 minus that, is 0.00700. So very, 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 very low chance. So the probability of me finding 7 or more red M&Ms out of 13 is extremely rare. It's probably not going to happen. It would be very, very, very unlikely. Now, what I want to talk about next is what happens if I have 1,500 M&Ms, right? 1,500 M&Ms. My chance of success is still 0.2 for getting a red M&M. Now, let's say I said, what's the probability you get at least 300 M&Ms that are red? At least 300. That would mean 300 or 301 or 302 or 303 or 304. Can you imagine how many calculations that would be? That would be many, many, many calculations. Even if I did exactly, even if I said, what's the chance that there are exactly 300 M&Ms? Well, I would have to do this. I'd have to do 1,500, choose 300, right? That would be 300 successes and 0.8 to the what? 1,200, right? So it'd be 300 successes, 1,200 failures. Now that first number is going to be enormous. 1,500, choose 300 is so massive that my calculator can't even do it. This number right here is absolutely enormous. It's just huge. I can't do it. So what I want to do, instead of using this model, since I really can't use this model, I'm going to go and use the normal model. Now, how could I transfer to use the normal model? Well, there's a couple things that I have to have. First, I have to have at least 10 successes and 10 failures. I got to have at least 10 successes and 10 failures. So out of those 1,500 M&Ms, I have to have at least 10 red and at least 10 that are not red. And that means 10 or more, 10 or more. Now, how do I check that? Well, how do I find out how many red M's I'm supposed to have anyway? Well, that's easy. That's where mu comes in. Okay, remember, mu will tell me how many M&Ms I expect to be red. Well, if I have 1,500 M&Ms and 20% of them are supposed to be red, then 1,500 times 20, or 20%, or 0.2, is 300. So that means I expect to have 300 red M&Ms. That's how many I expect to have. That would mean that the opposite of that, so that's n times p, right? N times p. N times q, or 1,500 times 80, would be 1,200. So that would be 1,200 M&Ms that are going to be not red. So I expect more than 10 successes, and I expect more than 10 failures. So successes, remember, to find the number of successes you expect to have would just be n times p. And to find the number of failures you'd have would be n times q. Now, in order to use the normal model, these both have to be bigger than 10. So if we go back to our last problem where we only had 13 M&Ms, 13 times 0.2 is only 2.6. Well, that's not more than 10, okay? So I would not have more than 10 successes in that case, so I couldn't use the normal model there. But here I can use the normal model. So what do I need to use the normal model? Remember, I need an expectation. I mean, how many successes do I expect? Well, that was n times p, or 300. But everything varies, so I also need a standard deviation here. And remember, the standard deviation here is n times p times q. I made that line a little too big there. Okay, so to find my standard deviation, that's going to be 1,500 times 0.2 times 0.8. This will tell me how much that's going to vary. So 1,500 times 0.2 times 0.8 is 15.4919. So 15.4919. So that means amongst 1,500 M&Ms, pretty big jar of M&Ms, I expect 300 to be red, and I expect that number to deviate by 15.4919. So now, if I wanted to ask myself a question, I want to say, what's the probability that there is at least 100 red M&Ms? Okay, what's the probability there's at least 100 red M&Ms? Well, I could kind of draw my normal model here, and remember, I'm very poor at drawing my normal model. Now, right smack dab in the middle of the normal model is what I expect. I expect 300 M&Ms to be red. And I know that number is going to deviate, and remember, it was about 15, right? So I'm not going to try to use too much math here, but this would be about 315, about 330, about 345. This would be about 285, about 270, and then about 255 here, okay? Now, I'm asking you for at least 100. Now remember, that means 100 or more. Please make sure that you understand that. Where does that fall? Well, I'll tell you where that falls. It falls way down here. In fact, the z-score for that would be 100 minus, I expect 300, divided by my standard deviation of 15.4919. That is a z-score of, let me calculate it real quick here. Going to be very, very, very low. Get ready. Negative 12.9099. That's an extremely low z-score. Okay? What does that tell you? It tells you a couple things. First off, seeing 100 red M&Ms in a group of 1,500 is very, very rare. Why? Because you're supposed to see 300. It's not going to vary much. It varies by 15.49. So, to answer this question, Now think about this, right? I want 100 or more. 100 is I mean, this doesn't even do it justice. It's way down here. Now, this is -3. I'm at -12. But I want to find the probability of 300 or 100 or more. That's going to be the probability of anywhere above this. This is going to be like, for the most part, 0.99999, right? So remember, I'm going to grab a normal CDF. I'm going to go from -12.9099, comma 99. And basically, it's telling me 1. It's telling me that there's extremely high chance of there being over 100 M&Ms that are red in this group. And that should make complete sense. Okay? Now, let's do another problem very similar to this one, right? Let's say there are, what's the probability of at least 350 red M&Ms? Okay, at least 350 red M&Ms. Well, once again, got my normal model here. Right smack dab is 300 in the middle. Up 1, up 2, up 3 standard deviations. Down 1, down 2, down 3 standard deviations. So where does 350 fit? Well, let's see here. Find the z-score. So that's 350 minus 300. So using that same z-score formula, divided by 15.4919. So let's see here. 350 minus 300 divided by 15.4919 is 3.22. 3.2275 to be more exact. Now, that is above 3 standard deviations. Remember, go look down here, right? Here was 315, here was 330, here was 345. This should be fairly rare, right? At least 350. I shouldn't really see this. 3.22 on my scale here is somewhere right around here, right? And I want to go higher because at least means higher. So for me to find the probability, I'm going to grab normal CDF. I'm going to go from 3.2275, comma 99, and I get that the probability is like that little tiny tail right there is 0.00062. So it's extremely small. So it's a very low chance of that. So again, remember, the normal model is pretty cool, it's pretty important, and it tells us the right smack dab in the middle is 300, and I can now get my standard deviation. That 15 will tell me how much I expected to deviate. So yeah, I expect 300 red M&Ms, but I understand that number is going to deviate. Now remember, when can you transfer and use the normal model in place of the binomial model? You must have at least 10 successes and 10 failures in order to make that transition. If you don't have expected 10 successes and expected 10 failures, you cannot use the normal model. It's just not a big enough sample size to support the normal model.